All right, so what we're going to talk about today is linear models. And we get to talk and do lots of technology this entire chapter. Shh. So we're going to find the line of best fit, which is also called the line of regression, which is also called trend line. Okay, so we talked about the types of models we have. And we're also going to use something called the sum of the squared residuals, and we'll do that later. So where we left off, we started by defining linear function. So essentially, you have a set of points, however many points. It doesn't have to be, since it's a function, there's probably an infinite number of points, such that you can write it as a straight line. B can be 0. Technically, M can be 0 also, so you don't really have restrictions on those. What's a linear model? An exact model usually is something that has to do with like dollars or something that's very consistent. Like I am going to buy, these are the number of shirts here. This is the number of shirts, and this is going to be, whoa, that's not how you spell shirts. And then this is the cost, right? So if they're like $12 each, this is 12, that's 24, etc. So that's going to be an exact fit, because it would go up perfectly like this. Notice I'm not going to buy fractions of shirts, so technically I'm not going to fill in between the points. All right, but that would be an exact model. An almost exact model, which is where we're going to spend a lot of our time. Almost an exact model would be just something that is kind of like this, and we're looking for a line that passes through all those points and describes the whole flow, kind of like a flock of geese, and we're just trying to figure out the path of the geese, because they're all going in a general direction. So a lot of things, almost an exact model, something like a projectile, a ball being thrown, that can mostly be described by a quadratic situation, a parabola, etc. Now an impressionistic model, we kind of did an example where we said the number of books here in the house, and they compared it to students' GPAs, and they realized that the more books you have, the more it goes up. And there is no reason in the world to believe that the more books you have, it actually fits and says the higher your GPA. There is no logical connection, necessarily. Not with the number of books. The culture for the type of person that has lots of books is probably a type of person who cares about the children's education. Therefore, that's affected. But it's not actually the number of books immediately. All right.
Didn't like Chicago
And we'll get more into specifics using your lovely TI and using Desmos in order to find what's called the trend line or linear regression line or line of best fit. So what I want you to do is, and we'll do the first one, we'll do this one right here first. Line of best fit, we can just do so by eye. Just trying to find a line that kind of nicely goes in between. Notice clearly that doesn't really describe it very well, and that doesn't describe it very well. So I'm kind of going to fudge around, and notice what I do. I'm kind of going to go in between, trying to keep it straight. I didn't like that one. I'm going to erase it. So I'm going to try another one. Again, trying to keep my line straight. Notice I may or may not go through any of the points. It might not touch a single point. It might touch almost all of them, okay? But the line of best fit just kind of is like the average line. So please take a moment and attempt a line of best fit for each one of these. Attack, kill, destroy. Your best fit might not be the best fit. So we're just going by eye to kind of figure out stuff. And notice I'm kind of making it go that way. Now this might be a little bit off, because when I consider this, I have 1, 2, 3 above and 2 below. So maybe adjusting it slightly more. We're trying to consider like the distance, the distances there as well, seeing if there's a better fit. We're going to talk about specifically, and I'm not saying the distance to the line. I'm not talking the distance to the line. I'm saying like the distance straight down or straight up. Down or up, and we'll get to that later. That's called the correlation coefficient and residuals. I know, residuals right there. Very fun. All right, so maybe yours looks like this, but notice that this one does have what is called a negative correlation. A negative correlation. That is, as these go up, this one goes down. As the number of As the number in the set here goes up, these also go up, so that's a positive correlation. Next up, this one here is also a positive correlation, and if I had to take a guess, it'd be something like that. Notice this one probably goes through 0, 0. Doesn't have to, but kind of does. And this one's nice. This was almost an exact fit, but not perfectly. And almost exact. Which would mean this would have a very good correlation. And we will talk more specifically about what those numbers are, how to figure out what a good correlation is. Yes, I did. All right, so let's take a gander here. And this section that you're going to have be working on is just the line of best fit, is just the line of, quote, best fit. It's just by eye. They just try to make everything go through it, okay? So we're not going to get the exact one yet. We're going to show you tech tomorrow or the next days how to do that. So let's look at this. The price of diamond rings sold in Singapore. No date on this, but it's probably 10 or 15-year-old data. So a carat would be 1 carat, so this is 0.18, so not even a fifth of a carat, and it goes for $702. Slightly lower is slightly lower. Notice I have a quarter, 0.26, and I get almost $1,000 for the diamond ring. So notice it's not just the diamond, there's other material in it, probably gold as well. So that's why this one, it's a 0.25, is more expensive than the 0.26, probably because of the other material. So notice it's kind of scattered, but it certainly goes up. Now, if we were to think about what this is, it's not an exact fit, and it's not impressionistic. Why is it not impressionistic? Because we would expect that the heavier the diamond is, what do you expect? The higher the price. So this here would be that second one. Almost an exact model is what this would describe. So find an equation of the graph which relates the weight and the price. This part, do you guys remember from Algebra 2 days?
It's algebra.
Where you were given 2 points, and I'm just going to make these points up. You were given 2 points, and you were told to find the equation of the line that crosses through those. Let's refresh what our steps are, which might make a good question over there. What are the steps to finding from 2 points? So from 2 points to an equation, and more specifically a linear equation. Number one, what we need to know what our slope is. Sometimes we're given the slope. Sometimes we have to calculate the slope. So we're going to use our super secret formula where we are going to say y2 minus y1 over x2 minus x1. Rise over run. Essentially, this is going to be our rate of change. How much something changes from one term to the next. Next, we're going to choose 1 point, and it doesn't matter which one. Choose a point on the line. Next, number 3, we're going to substitute this in, and if you recall, point slope form. And point slope form looks like this. Y minus y1 equals m times parentheses x minus x1. And this is called point slope form. It's sort of a crazy name because the reason it's called point slope is because you have a point and a slope. Crazy what they do with that. And the last thing to do generally is we're probably going to convert this most likely to slope-intercept form. Slope-intercept form. Tell me y equals mx plus b. All right, so we've got these 4 points, or 4 steps that we're going to do. Yay! So I need to first locate 2 points on the line. Not points, not this point right there, because that's not on the line. That is one of the data points about the how much it costs, but I want to know the points on the line. So I have to find the best possible points that cross through. So notice here, this looks pretty clean right here, because it's right on the corner. Notice it comes through, see, it comes here and comes here, the crosshairs there. So that's a pretty nice one. And I'm going to look for another pretty nice one. Looks like this guy right here is pretty nice, right there. Now, it's not perfect. It's not exact, okay? So I have to do a pretty good estimate about these. So let's just estimate what these guys are. So this one here goes down to whatever that is. We'll find that in a second. And it goes all the way over here to 1400. So this one here is, what would that be? So if that's 0.3 and that's 0.4, that's 0.3. 1, 2, 3, 4, 5. 0.32 is right. Good. So 0.32 yields me 1400. In other words, on my line, it's not the data from the chart. It says that if I have a nearly 1/3 carat, it's going to be $1,400. Okay, now another one here is 0.18 gives me 600. 0.18 is $600. So I'm going to take those 2 points down below and start walking through the steps. So I'm going to rewrite them down there. All right, so let's do this. First step, I need to find my slopums. So I take my $600 and I'm going to subtract the $1,400. 600 minus 1,400. Now, of course, I could have gone the other way around. That's fine. And then I take the 0.18 and I subtract the 0.32. 0.32. Now, if I were to multiply this out or fractionize it or whatever, because we're dealing with actual dollars, I'm going to get out of the fraction world because ultimately we're talking about how much per carat we're going to be paying here. So let's just pull out our handy-dandy calculators and multiply that or divide that real quick. So here's what my M is. My M is approximately 5,714. Let's just leave it in whole dollars for now. And next up, so that's step 1. I found the slope. Now I'm going to choose one of the points. It doesn't matter which one. Maybe I want to deal with the smaller numbers, so I'm going to choose this point here. I don't have to actually write that down. I just have to keep it in mind. Now I'm going to substitute in y minus the 600 equals 5,714 times x minus 0.18. And now it's probably best to put this in function form, or another way we say it is slope-intercept form. So I'm going to distribute out the 5,700, and I'm going to add the 600 there. So I'm running out of room, so I'll do that over on the side here. You can do it wherever you would like. So y minus 600 equals 5,714x minus, and now I'm going to finish this up by adding 600 to both sides, minus 42852. So please take a moment with your partner. What do the numbers mean there in the context of this problem? Go. So if we were to interpret this line, we would say that $5,714 per carat. So very few rings are a full carat. Most rings are going to be, especially wedding rings, are going to be fairly small. And does anyone have any clue what the negative number means? What does the negative 428? Which almost doesn't sound like. What if you had zero? What if you bought 0 carat? What would this say? That you earned 412. Right, so that doesn't quite make sense. However, so whatever we're trying to figure out, I'm not sure what that means, but that's probably the deduction they give you. The deduction they give you for buying a larger carat or something. So, what we do is when we take the y equals 5714 times 0.05 and we subtract the 428 point whatever, what do we get? What does that yield us? You have a question? So the function evaluated at 0.05, 1/20th of a carat, would give us something like a negative $100. So that means you go in there and you buy this ring, and they're going to pay you $100 to take it off their hands. So, Part D says, why is the data? Why is the data not our line of regression, but why is the data not a function? Well, what about this chart or the table or the graphed out part? What about this shows me that it is not a function? So if we look here, 0.16 gets me to 513 there, but notice 507 there. 0.16 gives me a 498. Again, that's like punching an L into your computer and getting out an L, then doing it again and getting out a Z. And you would say something's wrong. Okay. Now, the last thing we want to look at is how to use the line of regression. So let's say you have a bunch of data, boop, 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 and you have a line of regression that goes through that. Interpolation, notice the word inter, means you have this set of data, and notice it's the red points that I put on here. These are so interpolation says this. What would my data look like if I go between the data like this? Or what would I expect this many carats to be? Or what would I expect this one to be? Notice that it is in between the data points there, in between some data points there, in between some data points here. So hence the word inter. All right, so that's only looking at the data that's encompassed by, or like a projection based on the data I have, that's inside that data, within. The next one, so by extension, what do you think extrapolation means? Outside the data. So for example here, can I make a prediction about what it's supposed to be way over here? Notice it's outside my domain of the original data. So that is extrapolation. And notice that you can extrapolate in both directions. You can extrapolate a low or high depending on what it's asking. So an example of this would be, what if you have a bunch of data about the cost of houses going up, the price tag or the median of housing in an area, and you want to know what the housing price is going to be in 10 years. That would be extrapolation. But if you were missing some years, maybe you had 1999, 2000, 2001, 2000, boom, but then you had a gap of 4 years, and then you had a bunch of data there. The interpolation would say, oh, let's help fill in that gap.